Okay, 3:30. Right.
Yes, we're good.
All right, good to go. All right, so hi, everybody. Good afternoon. Thanks for staying and coming to our session. My name is Pam Lahoud. I am a program manager on the SQL Server database engineering team.
I'm Pedro Lopes. I'm also a PM in the same team as Pam.
And if you do want to talk to us after, Twitter is the easiest way to get to us. We also are on a team that's sort of informally, used to be formally known as the Tiger team. So you can also tweet at MSSQL and you'll get the whole team.
Yeah, so within the team, I usually take care of, I focus on the relational engine. In other words, that means everything that makes your query stick and actually return results to you and do it so in an optimized fashion.
And I work on the storage engine, so things that have to do with reading and writing I/O and TempDB, which is, if you've worked with SQL Server for a while, probably you want to lose my number. Okay. Okay, so what we're going to talk about today is performance tuning. It's not just for DBAs. So if you've seen Pedro and I speak at other SQL Server conferences, a lot of what we talk about is sort of geared towards database administrators and how to tune queries once they've been written. But what we want to talk to you about today is what can you do to write good queries in the first place? What can you do to make sure that your database code is efficient before it gets to production? And we want to talk about some best practices that will help you write good code. So this will be two sections. The first will be some application design patterns. So one is ORMs, or relational mappers, entity framework being probably the most common for .NET folks. And then a little bit about being cloud ready. And then we want to talk about T-SQL best practices, and we'll have a little shameless plug for you later.
Yes. We can't cover the entire surface area on that we'd like to talk here, so we just picked a few like nasty examples that we actually see fairly frequent out there in the field.
Yeah.
But there's plenty to follow up.
Okay. Right. So without further ado, let's start with some application design patterns. So the first one, to ORM or not to ORM? That is the question. ORM stands for Object Relational Mapper. How many of you write code using ORMs? Yeah, that's what I thought. How many of you are using Entity Framework? Something else?
Basically the same, right?
Yeah, almost the same. Something
number.
else. Hibernate or some of the other ones. OK,
Health
so we've got some other.
Stuff like that, OK.
OK, so I'm kind of generally talking about ORMs, but I've had the most experience with Entity Framework, so I'm going to kind of lean towards that. And you'll notice on the slide there's a little short URL to an Entity Framework perf. This is a page that gives you a whole bunch of recommendations about performance for using Entity Framework. But the question that we're going to talk about here is one that's kind of become a war between developers and database administrators. Because what do developers like? They like to write code. They want to write code first. They like manageability. They like agility. They have coding expertise, client coding expertise, .NET expertise. They don't always have T-SQL expertise. So how about your DBAs? What do they like? What? Control.
Cache? Someone said cache?
Pat? Bash?
Oh, batch, okay.
Oh, batch,
right.
batch. I thought you said bash. I'm like, why would a DBA want bash? OK, batch. Yes, they want batches. They want stored procedures. Mainly, they want performance. And performance.
And also?
And also performance.
Yes.
Right? So that's what your DBAs are after. And when you use an object relational mapper, it's not always easy for them to get that. And if you don't have a DBA to tune your code, then what?
You'll have to do it.
Yeah, either you'll have to do it or no one will do it, and then your application won't scale very well. So we'll talk. So a few of the arguments that I've heard from developers, and that I think are, by the way, I think very valid arguments. And I want to make sure that the point you get across from this slide is not that I don't want you to use ORMs or that I don't want you to use Entity Framework. It's not that at all. It's just that it's not the end of the story. It's not a one-time choice. So first, the argument I hear is application logic belongs in the client layer. Again, a valid design pattern. Agility, I want to do code first. And this is a big one, because we're developing applications rapidly. We have lots of applications to maintain. And doing a code-first design allows us to quickly and easily do that, especially if we don't have a dedicated database developer or an in-house DBA who can review our code, who can give us best practices, who can do the tuning that's necessary. So sometimes it's just a requirement we have to use Entity Framework. And I see, or other ORMs. And I see this is basically the world we're living in today, and it's only getting bigger and bigger. So why don't your database administrators like this? Well, the first thing is, when you have application logic in the client layer, your application tends to be chatty with the database. You're doing a lot of back and forth. You may be doing a lot of looping. You may be using cursors. You may be doing a lot of fetching of data over and over again, and sometimes that can get overly chatty. And it also keeps you from being able to use stored procedures, for example, which allows you to just keep the data up in the database. So maybe you get some data, you bring it down to the client, you do some stuff with it, you send it back, you do some more stuff, get some more data, join it back. You end up going back and forth a lot more. If you just wrote a stored procedure, everything would stay in the data. You wouldn't be shipping data back and forth. So another thing is ORMs generate spaghetti T-SQL code. And in the client layer, it looks awesome. It's not spaghetti code in the client layer, but once it gets to the database, it's like massive. And it's all kinds of like crazy views sometimes. You may be joining lots and lots of tables. It tends to depend on how complicated your object model is, but I've seen some really heinous entity framework queries, and they don't always perform bad. I don't want to say that those queries perform bad. They may perform great, but they're really hard to diagnose. So when I start having a performance issue and I'm trying to pick apart this really complicated EF query, it can be challenging to tune. And also, it can add additional complexity that is maybe unnecessary, especially if you're hydrating an object model with data that you don't actually need, and you're joining in all these extra tables, you may not even be using that data. So there can be some spaghetti code on the database side. And the last thing is, we don't really have a lot of control over making performance changes. So if the client is generating the T-SQL code and I find a mistake that's made that needs to be adjusted by rewriting that query, I don't have the ability to do it. I either need to figure out how you can rewrite your client code to fix it so that Entity Framework sends the right query, or I need to replace it with a stored procedure. Okay, so that's some of the reasons why database administrators are very resistant to the arguments. Now, here's the thing. Both arguments on both sides are very valid. So where does that leave you? You need to be somewhere in the middle. So the recommendation I generally make is do the code first design, but then do some tuning later. When you're done with that design, take a look at the queries. Just because you're using an ORM and code first design doesn't excuse you from looking at the database layer. So take the time, look at the queries that are executing, and look at the most expensive ones, the ones that are executing the most frequently, the ones that are using the most resources, and take some time to examine those and see if they can be done better. Are there maybe a few targeted places where you have super complex queries and they'd be better served with a stored procedure? Is there something you can tweak in the object model? Can you do like lazy loading or something where you're not fetching all this data at the same time? Okay, so these are some of the things that I would recommend that you do. And the second half of our presentation today, we will cover some of the strategies that you can use to identify poor performing queries and figure out, where are some things that you might need to tweak queries a little bit, what are some things that you can do, and how do you find those things? More importantly, how do you find them in development before they get to production? Okay. So next one, are you cloud ready? So you may not be in the cloud today. How many of you are actually developing for Azure SQL Database? Okay, so we got a lot. Okay. How many have never seen a cloud database, never want to see a cloud database, always on-prem or die? Not that many. Okay, cool, awesome. So even if you're not—
On-prem on die was really strong. Okay.
On-prem, oh, sorry. Was that—
No, go on.
I forgot, we're being recorded.
On-prem or die. Go on.
Sorry. Anyway. So even if you're not in the cloud today, but you're thinking of moving there, even if you're not thinking of moving there, somebody at your company is, guaranteed. There are a couple things that you want to do. The main point here is to pay down technical debt, if you have any, or don't accrue it in the first place. So if you're writing a new application, some things to keep in mind for designing for the cloud. First is proximity. So when you're on-prem, that chatty application Yeah, it can suck performance a little bit, but you can overcome some of that with hardware, and you may not notice it as much. But when you increase the distance between the database and the client layer, that sub-millisecond ping time might go away, and this chatty application becomes a lot more of an issue. So we need to think even harder about things like caching, making sure that we cache data that doesn't change very frequently. Use stored procedures where you can. Like I said, if you've got logic where there's a lot of back and forth, and you can push some of that up into the database in a stored procedure and just make it a little less chatty, that's good. Avoiding looping logic. So let's say I have a shopping cart and a bunch of items, and I want to put it in that shopping cart. I've seen code where people, one round trip to the database, create the cart. Then one round trip to the database for each item that I want to put in the cart. Or the other way around, I'm purchasing the cart and I do that one thing at a time by looping. It looks fine in the object model, but then you go to the database and you're firing off 10,000 queries to buy one shopping cart of things. So be cognizant of that chattiness. And the last thing, return only the data you need when you need it. Don't just willy-nilly hydrate the whole object if you only need like one column. Okay, so make sure that fetching rows and columns you need only.
So no select star?
Yes, no select star. Exactly. Especially from a complex view that joins 8 tables under the covers.
Let's not go there.
Okay.
I guess me.
COGS. This is one that we throw around at Microsoft all the time. COGS, reduce the COGS. Cost of goods sold. So throwing hardware at the problem is a much more expensive option when you're in the cloud, because you're paying for it by month. You're paying for the compute that you use. So this isn't as easy as it used to be. So of course, you want to tune queries, reduce your CPU and your I/O where you can. Remove unnecessary tables and data. So make your databases smaller if you can. Only keep the data that you need. Get rid of extra indexes that aren't being used, that kind of thing. Just do kind of a once-over of your database, house cleaning. Marie Kondo, Marie, your database. This table bring you joy?
Yes,
okay.
A little bit.
And then, sparks joy, your table sparks joy, yeah. And then implement an archiving strategy. So a lot of times, the business will say, we need this data around forever and ever and ever, and we can't ever let it go. And then if you show them the cost of that, then they're like, maybe we only need 7 years. Maybe we only need...
And then a EU citizen comes in, says,
yes,
let go of my data.
Yeah, okay, right. And then GDPR comes in and you have to get rid of it all. So, so think about an archiving strategy and also identifying data for that reason that you might need to remove later. And then the last is containment. So your options for moving to the cloud in Azure are different depending on the technology you use. So if you just go to Azure SQL Database, you may not be able to do things like cross database queries as easily as you can. You may be thinking about replication or SSIS packages, or what other things do you have that go with your database that might also have to go to the cloud. And it's not necessarily that you can't use them. There's usually cloud versions of everything that you're doing. It just may require a little more development to get up into the cloud. So when you're making those design choices, just kind of keep that in mind. Okay. And then, of course, those will be extra cost. Once you get to the cloud, all those extra features tend to be extra cost. So it's just something that bumps up your COGS if you're not kind of thinking in a contained way. Okay?
Okay, so
yeah.
Speaking about moving to the cloud and being cloud ready, for those that raise their hands saying on-prem or die, there's actually a good news for you. There's actually good news for everyone, which is the SQL database engine. It's literally the same between on-premises SQL Server versions that you've been working on for many, many years and Azure SQL Database, which means that in our perspective, and this is a mind shift, a mind state shift, stop upgrading and certifying for a specific named SQL Server version. I mean, oh, my application was designed back in SQL 2008, so I certified for SQL 2008, which means that's not ready to move to the cloud. I'll probably have to go through a lot of redesign and recertification in order to put it there. Well, not necessarily, because where we want you to go is to a place where you don't need to be worried about the platform, cloud or on-premises, but also don't need to be concerned necessarily about the name of the SQL Server version that you certified on. And that's because If you can actually upgrade to the latest DB engine, be that on Azure or SQL Server, without actually having to change your critical applications. Because for the most part, you can actually have frictionless migrations, this is a tough word for me, with no code changes from your source, which right there can be, for example, the black one can be your SQL Server 2008, where you're coming from, and then the choice on whether to host that database that will serve your applications on the cloud or in another on-premises services is yours, but it doesn't have necessarily special concerns in what relates to the code that's running inside the database. And so it's actually the benefit of thinking about agnostically is that you can simplify the way you certify your applications. If they're certified based on the compat level, on the compatibility setting that exists in the database engine that will tune the way that code runs inside the database to the version that you set it to, then that actually allows you to move from SQL 2008 all the way to Azure SQL Database or SQL Server 2017 and not having to go through a process of recertification necessarily. Now, that also reduces upgrade risks, because here's the thing. In some applications, you need to, when you modernize, when you come to that point where you need to upgrade, you upgrade the database layer and the application layer most of the times in the same migration window. And that can increase risk, because if something happens, it may be, you may not be in an easy place to troubleshoot whether you have an issue with the database layer or the application layer as code changes and schema changes went about. So you can actually separate these two moments in time and have less disruption if you can, for example, upgrade the database layer first to work in either Azure or newer bits of SQL Server. And then once that's stabilized, then actually move the application on top. And you can do all this, so upgrading to the latest database engine, that's the key word here, not SQL Server or Azure SQL. You can do that with no code changes. And why and how? Based on something called database compatibility level certification. Now, we provide an ecosystem of tools that allow you to actually determine if you have any potential issues moving your code. But the main idea is this. Your database was certified in SQL 2008. Guess what? It actually wasn't. It was certified on something called DB-Compat, Database Compatibility Level 100, which was the highest that existed back then. Now, the point is, you can actually move to higher versions and still keep that compat level, which means that your applications can modernize and leverage the newer platforms and the newer technologies that we bring to the database engine without necessarily changing and recertifying your application code to work with the new engine. So that means that you can maintain backwards compatibility, and that also means that by keeping that setting from your database as the same as when you once certified on, that means that from a query plan perspective, which is usually where the risk lies, they remain the same. And a quick example would be this. If you nowadays handle a migration of your application from SQL 2008 all the way to SQL 2017, for example, it may be that a part of your workload, if you actually move the DB-Compat level all the way to the latest and greatest, you get into issues. For example, some part of your query's performance may regress, which is obviously not something you want. So the point is, you can actually move all the way up from SQL 2008 to the latest and greatest with Azure SQL Database and SQL 2019 even, and still keep the compat level with which you certified your current application on. If you look at this matrix here, look at the SQL Server 2000 R2, it's the third column there, where we introduced DB-Compat 100. Now, as the timeline progresses all the way to SQL 2019 and Azure SQL Database, that same compat level remains, which means that I can take my database that I once certified on 2008, place it on 2017 or 2019 or Azure SQL Database, keep the DB-Compat level there, and it just works. And now I can point my application there.
And more importantly, if it doesn't just work for some reason, we will support you.
Yeah, because it should. So if you actually find an issue in this scenario that we just laid out, then you need to call upon us. Okay? We'll work out the issues with you.
Mm-hmm. Okay. So maybe it's a good time before we move on to the second half. Does anybody have any questions so far on what we talked about? What is the best channel to reach us? Is that what you're saying? I think Twitter, What do you say?
Yes, for a quick question, I would say that. If you actually run into a support issue in production, then the medium would be open a support case. If you think you want us to have a closer look at what you open in your support case, tweet us or DM us the case number, and we'll lean in and we'll try to work magic as much as we can.
Yeah. Thanks. Okay. So the second half is more about writing efficient T-SQL queries. So whether you've written your own queries or you're writing your own queries, or whether you're using some kind of ORM and these queries were generated for you, now what you need to do is, hopefully before you go to production, when you're still in your testing phase, you need to take a look at how your queries are executing. What are they doing? And the best way to do that is to get an execution plan. Look at an execution plan. So actually run the query in SQL Server Management Studio or in Azure Data Studio and get the query plan. Some people call it an explain plan, execution plan, but actually look at the plan. And there are things you can see in the plan that will give you clues as to why a query may be performing poorly. Or even if it's not performing poorly, it will give you clues as to how it may perform when it gets to production. So there are red flags, or actually they're yellow exclamation points, that will give you a clue as to, hey, maybe when I get to production, this isn't going to work out so well. So what we want to talk about here is just a little bit of an insight into how the optimization process works in SQL Server. We've got a tiny amount of time, so we can't cover it all, but we'll try to give you just a little overview, and then we'll talk about some common SQL Server anti-patterns that can get you tripped up when you're writing T-SQL code. So if you're looking at execution plan and you're wondering to yourself, why the heck is SQL Server doing it this way? I created this index. This index is wonderful, and yet it's doing a table scan. Why isn't it using my index? There are lots of questions you might be asking yourself when you're looking at an execution plan. So why did SQL Server pick this plan? The answer is cost-based optimization. That's why SQL Server does everything it does. It's trying to find the cheapest plan possible. But keep in mind that it's finding the cheapest plan before it actually runs the query. So it's all based on estimation. So
Yes, and cheapest means typically the fastest.
Fastest.
Because it's measured in that kind of abstraction. So the first thing that SQL Server loads when it needs to optimize a query are statistics. Statistics are metadata objects that allow SQL Server Engine to actually have a quick view over the estimated data distribution in the underlying tables that your query will be touching. So it obviously wouldn't be possible for us to scan the tables to know how many rows our query would bring, because actually we had run the query by then, so what would be the point, right? So these are the building blocks for query optimization. Having statistics on every usable column on every single table that your queries use will allow SQL Server to be more precise when it does cost-based optimization. But that also means that this metadata needs to be kept up to date. That's where your DBAs come in, making sure that both the settings and some grooming jobs are working in your database to make sure that these are up to date. Outdated statistics means decisions based on wrong data. So therefore, guess what? Probably you won't get a good execution plan out of that. Then there's the notion of cardinality. This drives the optimizer because after it loads statistics and a number of other objects that we don't have actually time to talk about here, what SQL Server tries to determine cardinality, meaning the number of records that will be traversing the plan, and an execution plan is like a tree. So it traverses from the tables up until it gives us a result set. And this will be one of the primary data points that SQL Server will use to create the plan. Answering the question, how many rows am I going to retrieve from this table and this index?
So let's say that SQL Server estimates, okay, the cardinality of this table is 10,000 rows, let's say. That means how many rows are in the table, right? Your query says select star from table employees or whatever, where last name equals Smith. And so it uses the statistics to determine the cardinality, how many rows are going to come back that have a last name of Smith, and it can usually come up with a reasonable assumption. So let's say that's like 5 out of the 10,000 rows. That's good information, and if it's right, hopefully we can come up with a good plan. But if we don't have an index on that column, then it doesn't matter what the cardinality of the query is. I have to scan the whole table. So if you have the best statistics in the world and SQL Server makes perfectly accurate cardinality estimates, you still have to make sure you have the right indexes in place to be able to retrieve those rows quickly. And SQL Server doesn't automatically create indexes. It automatically creates primary key indexes, but that's it. So you define your primary keys and you get those indexes, but you don't necessarily get any other indexes, and you might need them for your queries. Example, even just creating foreign keys, we don't create indexes for foreign keys automatically. You actually need to do that. And then you may have other queries, really important queries, that have predicates that don't have indexes. And if they don't, no matter how accurate our estimates are, we don't have a good way to get that data. So you also need to make sure you have a good indexing strategy. And that's one of the things you can look at in your query plan. And then the last thing is sargability. Sargability is a combination of 2 words, and it's search arguments. And I just remembered that we had detailed slides, and you were supposed to check me if I'm talking too much.
Oh, yes, actually. Well, I did the same, so let's just move on.
Okay, so we'll just move quickly.
We have more on this later.
So no matter how good your indexes are, there are things that you can do inside the query that will force SQL Server to have to scan the table and not be able to use your indexes. So that's really the key to T-SQL anti-patterns. It's ways that you write queries that either mask the cardinality from SQL Server, so they make SQL Server unable to accurately estimate cardinality, or they impact the sargability, which affects whether SQL Server can use your indexes or not. So those are the 2 key aspects to query tuning at the T-SQL level.
So let's talk about these 2 key aspects a little bit more.
One more click.
Yes.
There you go.
There we go. Fancy.
Yeah, I'm sorry. I did.
So the cardinality is, in essence, an estimation of the number of rows, like I said, that each operation in the execution plan will retrieve. Now, it can be, for example, the select star from my table employees will start probably with the table scan, and then if I have a where clause that implements like where employee ID equals 1, then I have a filter on top of that until I get my result set. Each of those operations or operators inside the execution plan will have a cost, and that cost is based on the number of rows that are expected to traverse and come out of those operators. So it's, like I said, it's based on statistics metadata. So for example, if the statistics say you have 1,000 rows in a table and you actually have 1 million, guess what? The plan will not be correct because it's based on wrong assumptions. And assumptions are also made if statistics are not available. For example, there are constructs in SQL Server, like table variables, for example, that only exist at runtime. So therefore, because they're not physical objects, then SQL Server cannot maintain metadata on data distribution on those objects because they simply don't exist until you actually execute them. So they're not usable by the optimizer, and therefore we guesstimate. We make guesses on the number of rows that should be coming out of that. But all of this leads into, if you have poor estimations, those are generally the cause for poor execution plans or inefficient execution plans. Inefficient because they would be awesome if the metadata were accurate, but if the metadata is no longer accurate as it relates to the underlying data distributions and number of rows and whatnot, then guess what? The plan is not efficient for my current reality, right? The other one is sargability. And sargability is, like Pam said, an acronym for search argumentable. And it speaks to the extent of which a predicate, a where clause, or a join argument that you have in your queries can actually use an index to traverse and get to the information faster. Typically, that would mean to seek an index rather than scan an index, or at least to do a range scan, which is less than a full index scan. So if you have indexes that actually can service your predicates properly, then you have, hey, a good indexing strategy, because guess what? They actually address the way you use the database through your queries predicates. Non-sargable expressions, and we'll see a couple of examples of those, cannot be used to seek. So therefore, SQL Server will resort to scanning a table or scanning an index, a narrow index. But scanning may not be the best operation for for the query you're throwing at SQL Server, but because you lack the proper indexes, it's the only thing that it can do.
And more importantly about scanning that I want to make a note of, if you're scanning all your tables in dev, that may not be a big deal because your tables in dev maybe only have a couple hundred rows, maybe a couple thousand rows. But once you get into production, those scans can become a big deal. So it's important, even if the query doesn't seem to run slow in your development environment, it's important to look for these kinds of things because once you get to production, it could be an issue, and it also could impact scalability. As your data grows, these queries will get slower and slower and slower.
Yeah, think about the phone book. The phone book is a classic, if they're still around, right?
Yeah, I know. At some point, somebody's not going to know what a phone book is. Hopefully that's
does
not
everyone
now.
know what a phone book is this room? Hopefully.
Okay.
Good.
Now we're good.
So think of a phone book. A phone book is obviously indexed by last name, for example. So if I want to look up my name in a phone book that has, I don't know, 3 million pages, whatever it is, then actually having to traverse each page looking for my name is difficult. And it may not be difficult if I'm looking at a quick cookbook that comes with my microwave that has 10 pages.
Yeah.
But guess what? If I have to look through 3 million pages, it's a lot.
Yeah.
So if I can actually use have an index and then use it to quickly go to the place in the phone book that has my name and then there be able to traverse a single page and say, oh, here I am, then actually it's a much cheaper operation. That's where sortable arguments come in. If SQL Server has the right indexes and you therefore use search arguments that can map to those indexes, then it really speeds up operations. Now, non-sortable expressions can then slow down significantly the queries, typically through the sheer size of data that you're trying to read.
Right. OK. So the last part of our session today, we're going to cover a few common T-SQL anti-patterns that you may see in your code. And then the last part is a demo where we will walk through how to find some of these anti-patterns by looking at an execution plan and also by looking at the code. So implicit conversions, this is a super common one, especially if you're using an ORM, because I've seen if you don't have type parameter typing, you could really bump into issues here. So implicit conversions is one. Functions in the predicate. So in your where clause or in a join condition, if you're not joining on the actual column names themselves, but if you're applying some kind of function. Like with a leading wildcard, so if you're doing a like comparison or like a fuzzy matching and you have a leading percent or a leading wildcard, that's also can be an issue. Or in the where clause. This is sometimes OK, sometimes not OK. We'll talk about that. Composable logic, I call this the Swiss Army knife query or the all-purpose query. A query that you run it one way and it's a spoon and you run it another way and it's a fork. And then table-valued functions. So we'll go into more detail on all of these patterns. But the common theme for these anti-patterns is that they either hide SQL Server's ability to estimate cardinality, or they make the expression non-sargable, or sometimes both. Okay, so that's the key here. Expressions may be non-sargable, or we may not be able to do a cardinality estimate. So let's start with the first one, implicit conversions. The reason why I really like to talk about implicit conversions here is I used to work in our performance tuning labs at Microsoft, and I can't tell you how many times we had really bad performance from queries simply because the parameter data type wasn't correct. And so here's an example here. I'm just doing a basic select star. Oh, God, I told you not to do select star.
Just for demo purposes.
Put it on the slide. Just for demo purposes, try not to do select star. Select star from product where product ID equals 7. Looks like a perfectly simple query. If I had an index on product ID, should be easy, straightforward, no problem. Here's the problem. What if product ID is defined as a varchar, not as an integer? Seems kind of crazy. Why would you do that? But you never know. Sometimes we have legacy data. Who knows? But it's defined as a varchar. So when SQL Server executes this query, it doesn't throw an error. It just does an implicit conversion. It goes, oh, I'm sorry, you meant varchar 8. Let me just do that conversion for you. But here's the problem. It's not going to convert the 7 to a string. It's going to convert the product ID column to an integer. Okay? And then it's going to do the comparison. So if you have an index on product ID, that's awesome, but we're not going to be able to use it. This makes your expression non-sargable, because I have to convert the data type for every single row before I can make the comparison. I cannot use the index.
So the conversion here is done at runtime, and that's the
exactly.
focal point.
Exactly. It's done at runtime. I mean, we know that we have to do an implicit conversion at compile time, but we can't do it until runtime. So this becomes non-sargable. Here's why, because you would say to yourself, why wouldn't it just convert the 7? Why would it do that? The reason why is the rules of data type precedence. When we are comparing two unlike data types, there's a list of data types in order of precedence. We need to convert the lower precedent to the higher precedent. And when it comes to integers, we need to make sure that whatever string value is there is actually a number. Otherwise, we do need to throw an error. So we have to convert product ID to integer. We can't do it the other way around. So this should be really obvious if you're looking at the query that that data type doesn't match. But most times where I see this problem is one of two problems. Either you have a stored procedure or a parameterized query, and you're sending the wrong parameter type, or you have two tables with two different columns that you're comparing in your database, and you think they're the same data type, but they're not. Okay, so this happens a lot with maybe varchar and nvarchar. So maybe you did like a varchar conversion, or maybe one day somebody started creating nvarchar strings instead of varchar strings, and now you have this mismatch all over the place. That can wreak havoc. But more importantly, what if you had all varchar strings in your database, but you're using, say, entity framework? Entity framework sends all strings as nvarchar. So now, and again, rules of data type precedence, I have to convert the varchar to an nvarchar, so it's the bad kind of implicit conversion. Okay, so this is something you have to be very careful for. Make sure that you're sending the correct parameter types, make sure that your data types match, and make sure that if you have a database where you're joining different columns, make sure those columns are of the same data type.
So another non-sargable expression would be when you use functions in your predicate. Now, functions are also resolved only at runtime, which means that during the query compilation phase, SQL Server doesn't actually know what's the outcome of applying a function. So therefore, we can't really estimate the number of accurate rows that would come out of that operation. These are two examples here. Look at this select star from the person table, and now I want to look at everyone whose first name starts with a B, and what I'm doing here is I'm using the substring function to return only the first character of the first name column, and then where that equals a string B. The query on the bottom is very similar. I want to get all the sales from the year 2008, so I could logically just use the year implicit function to convert the order date into the desired year alone, and then compare that with my integer there. Now,
keep in mind, I just want to say, we didn't just invent these. I actually had customers come through the lab that had these queries. The first one was because everyone told me likes are bad, and I didn't want to use like. So they wrote substrings instead, which is much worse. And the second one was, again, this kind of functional mentality. Function seems cleaner. I don't want to do a range scan. It looks like spaghetti code to me, because it's big and long and ugly. If I just do this, it's much more concise and clean code. Remember I said spaghetti code? Sometimes spaghetti code in the database is good.
Okay, but now we're confusing, because sometimes it's good, sometimes it's bad.
Here's good spaghetti code. Go ahead.
One of the points is obviously you need to test.
Yes.
Especially because if you remember the earlier slide, code first, tune later. If after you code and you bring it into a pre-production system and you start testing, and some queries will just pop out as being poorly performant, you can take those and then start tuning and applying these tips and hints here. So I could easily turn these queries with these specific where clauses, these predicates that only resolve at runtime, and actually provide information to SQL Server to try to get proper estimations, so proper cardinality during the compilation phase by turning him into this. So a like isn't always bad, and I'll have an example after the next slide. For example, a like that starts with a string literal, can actually be used by SQL Server to seek on an existing index. And to resolve the other query that was using the year function, I can actually have, I know I can find the logical dates within the year, the first day of the year and the last day of the year. If I use a between clause, then it actually gets me the same logical result. But guess what? because it's been expressed as a pattern that SQL Server Engine can actually resolve when it's compiling the query. It can use all those statistics and to come up with accurate cardinality for the number of rows that are expected to come out of those expressions. Now, these two, and using the like example, the like with a leading wildcard is non-sortable. So if you actually use likes, and that's the example that Pam was giving, oh, I heard likes are bad. Well, yes, if you use them like this. If you lead with a wildcard because you're trying to do fuzzy pattern matching, then SQL Server will not be able to estimate cardinality properly because anything can have a B in the middle of the expression. So therefore, everything must be scanned. If I'm looking for where names start with B, then the bottom expression is sortable. If you need to do something like the top there, where you need to do fuzzy pattern matching, there are other technologies, even in SQL Server, that do this in a much more agile fashion. For example, full text search. Full text indexing it's a lot more flexible and much faster in doing these fuzzy pattern matches here. So that would be something you need to take a look at. And that's exactly what I said. So if you don't have a leading wildcard, then you can do a range scan at least. Because the bottom expression there with a B and a wildcard means that when SQL Server is looking at an index, the index will have, let's say, all the first names, but it can range scan only the Bs, where the first name starts with a B. So that's much cheaper than traversing the entire index, which may have millions or billions of rows.
Yeah, I was supposed to do the last one, so it's fine. You do this one. Keep going. No, you keep going.
OK. I'm sorry about that.
That's OK. Keep talking.
I just get on a roll. You know that.
I know.
I'm sorry. You need to kick me.
Roll, roll.
So or in the where clause. Now, this is another one that hurts sortability. If you look at an expression like the one you have right here, which is a little bit like trying to solve two queries in one, because I have two different predicates that are not necessarily related. So salesperson ID and customer ID. This one, because I have an or condition there, and it's so wildly different, will lead to typically a scan being used in the underlying table, in the sales or the header table. Now, if you change actually this to be a union, or if you actually know that these two wouldn't be able to come up with overlapping result sets, even a union all, that actually gets you out of a problem. Instead of an or condition, using a union in many cases can yield better results. Now, as anything, you need to test. It's not a universal given.
The other thing I want to point out is if it was the same column, so for example, if it was where salesperson ID equals 277 or salesperson ID equals some other number, that kind of or is OK, because that's basically like an in clause. So we're salesperson ID in a list of numbers. That's OK, because we can use a single index to do this. It's more likely when it's two completely separate predicates that are unrelated, two sets of data that are completely unrelated, because then SQL Server can't use one index. It might have to use two separate indexes, but the problem is it doesn't usually do that. It usually ends up scanning for one predicate or the other. So the union allows it to, we're basically forcing SQL Server, pick these two separate indexes and then intersect the set.
Which, depending on the size of your data set, can be much more
efficient.
Yeah,
it may or may not be more efficient. So this is one that you definitely need to test. In some cases, it could be hugely more efficient. In some cases, it may not. Question here. So the question is this just in the where clause, or what if you have it in the join? In the join as well. In fact, ors in the join, I mean, they're basically predicates for the join. And so that's also getting into that Swiss Army knife query I was talking about, the composable logic. So anything like that, because that or is not being really evaluated until runtime. So again, it's something that SQL Server can't necessarily estimate that cardinality correctly. So yes.
By the way, it also depends on the type of join. An inner join,
yes.
An OR clause in an inner join actually means the same. It will be transformed internally to a where clause. An OR condition in an outer join, that completely changes the game, and I don't think we have time to talk about that.
Yeah, we probably don't have time to talk about that. But yeah, we can talk more about that later. But yes, just suffice it to say, in an inner join, yeah, it would be the same problem. Okay. Yeah. Oh, OK, sorry. Now me. So I keep talking about this composable logic. This is one that I used to battle in the labs a lot. So what do I mean by composable logic or the Swiss Army knife query? What I mean is you have a single stored procedure or a single statement that does different things depending on the parameter value that you send. So if you look at the screen here, do I have a laser pointer? I don't know.
I don't think it works.
Yeah, it doesn't. Okay. So what I've highlighted in green here, so you can see I've got a parameterized query. I have a stored procedure, but this could happen with any parameterized query, where I send a salesperson parameter, and the default value for that salesperson parameter is null. So if I send a null, I want to get all the salesperson orders. But if I send a number, I want to get only the salesperson orders for that particular salesperson. So great, I want to write one query to do that because it's basically the same query, right? Why would I write two separate queries for that? Well, let's pretend I have 10 million salesperson orders. A query that returns 10 million rows is not going to have the same plan as a query that returns 10 rows, or even 100 rows, or even 1,000 rows. Okay? So this really should be two different plans. But I've written one query, so I get one plan. And it's probably not a good plan for either condition. That's what generally happens here. So this is the case, this is another one of those cases where spaghetti code is your friend. So a lot of folks will say, how do we solve this problem? Some folks will say, add a recompile. But what if this query executes like 100 times a minute? That recompile is going to drive your CPU through the roof. So we can't necessarily recompile every time. So what's the solution? The most accurate solution would be to move the conditional logic outside the query. Check if the salesperson parameter is null. If it's null, run this query. If it's not null, run this other query. But what if you have more than one parameter? What if you have like 10 parameters? Now you're talking about this massive stored procedure with this giant if clause. It would be huge, right? It would be unmaintainable. So your other option is to do dynamic SQL. Now, you've probably heard a rule. You've probably heard somebody tell you dynamic SQL is bad. We never want to do dynamic SQL. Why would we do dynamic SQL? We like stored procedures. Whatever the reason, sometimes dynamic SQL is better than writing that Swiss Army knife query or that Swiss Army knife stored procedure. And we can execute dynamic SQL as a parameterized query by using SP-execute SQL. So if you use this SP-execute SQL command, and by the way, when you write entity framework code, all the queries come in as SP-execute SQL. They come in as parameterized queries. So you can write dynamic SQL, and it ends up getting handled almost exactly like a stored procedure with reusable query plans that SQL Server can match in the procedure cache and with parameter markers. So this meets pretty much all of the reasons why you wouldn't use dynamic SQL. The two big reasons are performance and security because you're worried about SQL injection. This should solve both issues using SP-execute SQL. So with this, I build my query. I only have to build it once. And then I check my parameter values, and I just add to my predicate based on my parameter values, and I send an SP-execute SQL. Each different iteration of that query will be cached individually and be able to be reused. Okay? So this is, I would say, quote-unquote, good dynamic SQL. All right. And last but not least?
And then you have table valid functions. Well, much like table variables, these are constructs inside SQL Server that only exist at runtime. So a table valid function is, in essence, a user-defined function that its job is to return not a single value, but rather a table of values that can be consumed by subsequent queries. Now, this quick example here, I'm retrieving data from a user-defined function that returns a table. So it's a table valid function and I'm passing a parameter, in this case 25, that will be used inside the code of the TVF to return whatever the results that match that 25. Now, the problem with these sorts of objects is SQL Server doesn't resolve this at compile time, only at runtime. So the query plan for this is usually inefficient, or it was until recent versions. And that's because for a table valued function, because it doesn't have statistics, SQL Server estimates that only 100 rows come out of that table valid function. Now, if the table valid function returns 10 rows, 50 rows, 100 rows, maybe even 200, that's all fine, because there's some tolerance in poor cardinality actually leading to a bad plan or not. But if that TVF, that table valid function returns thousands of rows or millions of rows, then you're dead in the water. So this can be, this is an example of an STVF, so multi-statement table valid function. And you see there highlighted in green what makes it a multi-statement TVF. Now this is a simple example where I enter the employee ID, as you see there. And then at runtime, it will create this table variable or of sorts, the return find reports that has those columns there. And then I have a number of multiple statements that can be, for example, the if conditions that Pam had in the previous example. Now the point is, all this is usually very bad, especially because I just said we have fixed estimations. There's no real understanding of the amount of data that comes out of those functions. So one option can be many times to take those functions and spin it around as this different kind of function, which we call inline table valid function. Inline because for SQL Server, it very much acts like an existing table, some object that can actually be resolved at compile time, and therefore SQL Server can derive the cardinality properties from that object. And it's defined, you see the fundamental change as you see there, it still maintains the parameter, but as you see highlighted in green, that T-SQL notation makes SQL Server understand it's now a different type of table valid function, one that can return an actual table that SQL Server can resolve at compile time and therefore have real estimations of what comes out of that, like you would if you access any actual table that exists in your database. So the point is you should always use inline table valid functions as possible. Because
if you have to use a table valid function.
Yes, if you do have. The point is if you have table valid functions in your code today, and if they are multi-statement table valid functions, in many cases, especially when you have singleton queries or queries that can be expressed with a few case notations, for example, you can turn that into a single query, encapsulate that into an inline TVF that then SQL Server can use to actually derive proper estimations, and guess what? The result is you get a better plan for your query. SQL Server 2017, however, and Azure SQL Database will automatically inline the previous example of a multi-statement table valid function for your benefit. So turning your multi-statement table valid functions into inline table valid functions is still considered a good practice. But in case you are using Azure SQL Database or SQL Server 2017, guess what? We actually do some of that work for you. So what we'll do is when we encounter during the query compilation, when we're finding the execution plan, when we encounter an MSTVF, we just sidetrack. We go and populate that MSTVF to have an actual object on which you can see, oh, how many rows do I have coming out of this? And then take that information back into the optimizer and optimize the rest of the query with that real information in mind. So that really improves the situation where you have a lot of multi-statement table valid functions in your code, and you're having poor performance out of it. Just upgrading to Azure SQL Database or SQL 2017 just solves the issue in many, many, many cases. So now we're going to do a demo here that brings together some of these cases that we talked about. Oh, thank you, Pam.
Got it. You're good.
So this is a query that is looking at my fact order table. And I'm using, clearly I'm using a function here because I have parameters. And then I have another join with another table. And this will give me the orders and the descriptions for a report that I have on all my goods that I'm selling. So I'm going to click this button here. Let me bump this up so I can get the actual execution plan. This is probably something good you need to do once you're still in that environment. So make sure that you look at the actual plans and have real metrics on which you are measuring the execution of your queries. So I'm going to execute this, get the actual plan. Sorry, that was a bad one.
You hit the estimated, I think, by accident.
No, and I was disconnected in the meantime. Yes, I need to
And
do
now
the
you're
right
in the wrong
database. That's all good. This will be Wide World Importers DW. So, okay, it executed in roughly 2 seconds. And I have here my result set. And let's look at the execution plan. I'm going to put this a little bit bigger. Okay, so looking at the execution plan, remember Pam said something about yellow markers? Here they are. Here's a few. Yellow markers are warnings. Warnings that SQL Server puts right in your face that says something is wrong here. Or at least this is something you need to take a look at. Look at this one, for example. there's a warning that says that this operator spilled to tempdb and read written a number of pages to tempdb. Guess what? If the operation doesn't fit in memory, if we can't use everything in memory, we will write to disk, to tempdb, and what typically I/O is slower than memory.
Not only that, but tempdb is shared. So if you have multiple databases on the system and they're all spilling to tempdb, you can start getting contention there because we have only one tempdb.
So I can see another hash match operation to resolve one of the joins that again spill to this. So it's a different spill. Let me actually bump this a little bit better.
Yeah.
There you go. Where you can see here, it's a different operation. They also spill to disk. And this is all based on estimations. Why? Because SQL Server, as you look here, on my table scan, and this table scan is done on my MSTVF, my table valued function. Look at this. SQL Server only estimated 100 rows would come out of that object because it's a fixed estimation, because this table valued function did not exist, was not materialized at compile time, only at runtime. So therefore, we see that 100 rows were estimated, but guess what? 100,000 were output by that. And because SQL Server only estimated 100 rows would come out of that, that also drove, amongst other things, the amount of memory that SQL Server thought would need to resolve that query.
And it ran in 2 seconds on Pedro's laptop, but I guarantee you when you get this thing to production and you have 100 different instances of this query running at the same time, it will not be that fast.
Yes, exactly. And we see that then that decision here of having 100 rows, of thinking we would have 100 rows, drove decisions up to 3, because this is a tree, as you can see here. And also 100 rows were estimated out of this join, 1 row estimated out of this join, and so on and so forth. So clearly an inefficient plan from that standpoint. How can we solve that? Now, we have learned that we can turn a number of MSTVF, so multi-statement table valued functions, into actually inline table valued functions. So I took the query that was inside my, actually let me show you because I didn't. The MSTVF is here, so returns a table that only exists at runtime. And this is the query that was inside. So insert into that table created at runtime this query. So I took this query and put it inside a inline TVF. So that inline TVF still takes the same parameters as expected, but returns a table, much like a physical table, rather than a table variable. And by creating this, let me just make sure I actually have it. By creating this table value function, I'm now running the exact same query, but going against my new inline TVF rather than my MSTVF. And when I run the query, first of all, it's done. So it didn't even took took 2 seconds that it did before. It actually didn't even account for 1 second.
So less than a second.
Less than a second. And look at the execution plan. It's much simpler. It's cleaner. And I don't have those warnings on those hash matches. Also, look at the estimations. They are now much closer to the number of rows that I actually got. And because I don't have the warnings here, which means that I didn't use a tempdb, and this query just by definition ran much faster.
So not only was it much faster, but it's more scalable, because now we're not using that shared tempdb resource. We're not spilling to tempdb. Less I/O, less conflict with other things running on the server.
And this also means that SQL Server was able to better estimate the amount of memory to take out of the server.
Right, that too.
So instead of you thinking you could run 10,000 queries a minute and they all start using tempdb, you now have a much better accurate estimation of what you can expect in terms of performance from your server. But oh, I still have one here. Let's look at this with more detail. I still have one warning here, and this warning, oh, it's something you mentioned before, Pam. It's an implicit conversion. And in this case, we're implicitly converting to a varchar 12 the column picker key. And SQL Server is actually telling me that, hey, this implicit conversion affected my ability to do a seek plan. That means to actually use an index to seek on, and therefore I scanned it as a result.
Non-sargable. So it's telling you this is both influencing your cardinality estimate. I wasn't able to estimate the correct cardinality, and it's non-sargable. So even if I could estimate the cardinality, I can't use an index.
Yes. So this falls upon us that we wrote the query to try to find where this is and solve it. So now let's look at the query that I have here. And So the implicit conversion, again, was on the foo table, on the picker key column. My foo table is foo. I'm sorry, foo. Foo is foo is the MSTVF.
Terrible aliases.
I'm sorry.
Okay.
This was written in a hurry.
18 seconds.
So I have my fact order table, and so the column is on that fact order table. I can expand my database tables here, and if I go to my fact order table, guess what? The column on picker key is
It's up where the keys are. There you go.
It's an integer. So because of rules of data precedence, I had to convert an integer that lies lower in the data precedence table to a higher precedence varchar. So that means that for every record in the picker key table, for every record in the picker key table, I convert it to an integer to be able to compare with my my predicate. Now, where is that predicate expressed? Oh, it's right here. Picker key like 0. Now, we mentioned that you could use a like and not if you don't have a leading wildcard, because you could use the index. Yes, but that's only in the case where you're not doing implicit conversions. In this case, we don't have a leading wildcard, but we are doing implicit conversions, so therefore, this actually doesn't make sense. So one thing I could do, if I determined that this could actually be expressed by an integer, as my database actually has an integer in its table, is to change the query into this, where picker key equals 0 rather than like 0, even though it doesn't have wildcards. And when I do this and run this query, looking at the execution plan, there are no longer warnings here. And as expected, we don't have warnings in the hash matches as well.
And the estimations are
more than that. The plan also slightly changed, because if you look at this shape, the shape is now a better form tree, meaning that it's even a better plan just because I removed that information and SQL Server was able to further optimize the plan to read the data for my data set. So,
7. Or 5.
Oops, 5.
There you go.
There we go.
Got it. All right. So we're out of time. Sorry, so thank you. But we just wanted to give you a few more extra little tidbits at the end here. So one is we just had our new book published literally this week. And so we talk about these anti-patterns as well as many, many more anti-patterns, and we go into much more detail on how the optimizer works and how you can analyze execution plans. We talk about a lot more nuggets of information you can get from execution plans in this book. So you can get this either from Amazon or from Pact, and we have short URL there. We also have some other demos that you can browse through. So the first short URL data demos, that should be all of the demos from the Azure Data team that were at Build this week. And then IQP demos, these are from our Tiger toolbox on GitHub. Both of these are GitHub links, by the way. And these are about intelligent query processing, so a lot more about the query processor. One last shameless plug. Tomorrow we are doing a past marathon Thursday, after Build, Thursday. Pedro will be doing a session, and we have a few other sessions from Microsoft coming to you from SQL Pass. That's a free event that you can register for. And last but not least,
thank you very much.
Thank you very much. If you have any questions, please feel free to come find us.